Welcome to the lecture Digital 3D Documentations in Archaeology. In the first lecture, we will get a general overview of the topic of digital 3D documentations in archaeology and learn about good arguments for their use. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. Colin Renfrew and Paul Bahn, in their classic book on archaeology, sum up the most important task of an archaeologist. But it is all the painstaking task of interpretation so that we come to understand what these things, and this refers to the treasures of the past, here mean for the human story. Excavation does not pursue an end in itself, and as a rule, it is not about treasures in the sense of special objects or material values, but the collection of large quantities of objects. It is research data for the reconstruction of processes of the human past. No sword, no coin, and also no uncovered excavation situation have a scientific value taken alone if the temporal, the local, and the historical reference are missing. As a rule, excavation situations and finds are drawn and thus interpreted by humans and reduced to the essentials. The contents are placed in a contemporary historical context by means of circumstantial evidence and comparable finds, and thus acquire their scientific value. This human task cannot be accomplished by any computer today or in the near future. Nevertheless, computers and their methods and applications offer in many places numerous, so far hardly exhausted possibilities to support this process of knowledge. The interpretation of archaeological finds and features is very often closely connected with their position in space and their spatial relations to each other. Therefore, the digital representation of space by modern computer graphics yields a great potential for archaeology. We will have to transfer this maxim directly and always question ourselves what value added various aspects of 3D documentation can provide for archaeological interpretation. This also applies to typical materials of 3D documentations, such as photos, videos, and also 3D models, without a place, a temporal, historical context. These products remain scientifically meaningless. Various reconstruction methods can be used within a digital 3D documentation. We will discuss the different approaches in the following sections. However, 3D documentation in an archaeological context does not only include the reconstruction method and the result thereof. A 3D documentation includes the choice of methodology, the planning, execution, and creation of a 3D model, as well as the archiving, raw data and models, and publication of the interpretation in a scientific context. We will learn about the various aspects of 3D documentation in this course. But before we start, however, we must first clarify and define the term 3D reconstruction. First, we need to clarify the important term 3D reconstruction. There are two fundamentally different approaches that can be described by the term 3D reconstruction in the context of archaeology. In the first case, digital 3D models are reconstructed by a human using digital tools based on excavation plans, drawings, traditional descriptions or illustrations, and analog finds. This is what we should really call reconstructive 3D modeling. In the second case, camera or measurement systems and computer algorithms are used, which can mathematically derive the object structure via the read-in data. In both cases, the result is a digital 3D model. In the further discussion, we will exclusively consider the second case, in which image captures are algorithmically merged into digital 3D models, and use the term 3D reconstruction as a synonym for it. Let's start by looking at some different techniques of 3D reconstructions in archaeology. A wide range of different procedures and devices are available for 3D reconstruction. The presented methods are sorted according to their costs and are briefly described in the following. Certainly, terrain models can also be systematically created using total stations, but here LiDAR and photogrammetry offer the much better alternative. Therefore, surveying with a total station was not listed here. Structured light scanning uses a projector to project patterns of light structures onto the surface of an object, while a camera captures these reflective patterns. By analyzing the deformation, the system can reconstruct the 3D geometry of the object. The cost of structured light scanners can vary widely, but they are generally more expensive than traditional laser scanners, but less expensive than high-precision laser scanners. There are already mobile devices that can be used to scan objects quickly. Structured light scanning allows large areas to be scanned quickly and provides highly accurate 3D data that can be used in archaeology in the 3D reconstruction of objects. In this video, we see the use of a structured light scanner in the Saxony State Office for Archaeology. Through different light patterns and their reflection, the surface structure can be derived. There is already a wide variation of color and light patterns used in structured light scanners. Photogrammetry is based on the analysis of photographs to derive the spatial geometry of objects or environments. By analyzing common image features, 3D models can be created. If image selection algorithms are used, videos can also be used for 3D reconstruction. For this purpose, the photos relevant for the reconstruction are extracted from a video stream. Photogrammetry is widely used in archaeology to record surface details of objects, archaeological sites, and terrain features. Here we see an example of the royal tombs in Cyprus, captured with a simple smartphone and processed in reality capture. The briefly presented methods computer and neutron tomography, ground-penetrating radar, laser scanning or LiDAR, structured light scanning, reflectance transformation imaging, and photogrammetry and videogrammetry can be excellently applied in the archaeological context. With computed tomography, neutron tomography, and ground-penetrating radar, we have two non-invasive methods at our disposal, in which objects can be transilluminated and terrain can be examined with the reflectance of electromagnetic waves, respectively. For the other invasive methods, the objects have to be excavated or opened, because only what is visible is digitally reconstructed here. I would like to briefly summarize the invasive methods again. Laser scanning uses special devices that systematically scan the object surface with the aid of laser beams. Here, for example, the scanning rate can be set via the distance. In structured light scanning, various structured light patterns are projected onto the object surface and recorded by a camera. The surface structure can be derived from the projection pattern of the light stripes. In reflectance transformation imaging, several images are taken with different light source positions for a fixed camera. From this, the material properties can be derived with regard to the reflectance behavior. If this is combined with photogrammetry, for example, 3D models can be generated and displayed with different reflectance properties. In photogrammetry and videogrammetry, the object structure is derived from common visual features that can be seen from different camera shooting positions. Classically, we count laser scanning, structured light scanning, reflectance transformation imaging, as well as photogrammetry and videogrammetry among the methods of 3D reconstruction. Here, the objectives of the 3D reconstruction and the available equipment or finances must be clarified in advance. Photogrammetry or videogrammetry offers by far the simplest and cheapest access to the topic of 3D reconstruction and can be used directly by anyone without major hardware and software requirements. All that is needed is a camera, which has become an essential part of everyday archaeological documentation anyway. Scanning with laser or structured light is ideal for archiving objects in museums, for example, because of its high precision. With photogrammetry and videogrammetry, a method is available that requires only a camera. Here, the imaging strategy, the object distance, and the selected lens determine the precision of the 3D model. For invasive methods of 3D documentation, the objects must be exposed or cleaned. With computed tomography or neuron tomography for objects and ground-penetrating radar for terrain structures, non-invasive methods for 3D documentation are available. In contrast to reconstructive 3D modeling, we define 3D reconstruction in this course as follows. In 3D reconstruction, distances of object features are measured or estimated from a set of electromagnetic wave, laser, structured light or image data and used to derive a digital 3D model. In this lecture, we will exclusively consider photogrammetry or videogrammetry, respectively, in which image recordings are algorithmically merged to digital 3D models, and in the further course we will use the term 3D reconstruction as a synonym for it. Photogrammetry, especially close-range photogrammetry, has established itself in archaeological documentation work. Photogrammetry is a highly precise science with a long tradition, which had its beginnings already at the end of the 19th, beginning of the 20th century. Here, with the help of photogrammetry, the position and shape of objects can be reconstructed from images. A very important extension to photogrammetry is videogrammetry. Videogrammetry extends photogrammetry by the processing of video recordings and deals with algorithms for intelligent image selection. We will talk about the advantages and disadvantages of both strategies later on and see how the advantages of both strategies can be combined in a meaningful way. In recent years, and by now decades, development in the field of real-time robotics has progressed far in terms of camera-based systems. In a fraction of a second, vehicles can recognize traffic signs and road situations, and in some cases, react autonomously to them. The precise localization of a passenger car is greatly aided by GPS and the relatively known road situation. Driving situations with parked vehicles and pedestrians, however, can only be mastered with real-time detection. A very active research focus in this context uses structure from motion and pursues simultaneous localization and mapping solutions to localize oneself in self-generated maps or 3D models of an environmental situation. The boundaries between these real-time applications and photogrammetry methods are now becoming blurred. Both benefit greatly from this. The use of such methods also makes sense in the underwater sector, because here, in contrast to an aerial survey with multicopters, we cannot easily fall back on GPS data for position determination. We see here, from left to right, 3 temporal stages of real-time 3D reconstruction during a diving session. In the upper part of the image, stable image features of the current image can be seen in each case, turquoise dots. If these points are identified in subsequent images, here with green rectangles, they represent points in 3D space. In the lower image section, the camera positions, here with blue rectangles, and the resulting 3D points with red dots can be seen in each case. Before we really want to get into the field, we need to be aware of one fact from the beginning. Unlike a photo, which is a two-dimensional representation of reality, a 3D model is the result of a 3D reconstruction pipeline in which various processing and interpretation methods are processed in sequence. We need to understand that there are very many different methods and procedures that can derive one or more 3D models from a set of images. There is one important fact here that we cannot understand soon enough. The 3D reconstruction process is a snapshot of current algorithmic procedures and methods and does not necessarily provide deterministic results. No deterministic results are guaranteed, even when using the same input data and an unchanged process chain with the same parameters. This is due to the fact that within the methods, randomness often plays a large and decisive role in evaluating the large amount of data of millions and millions of points with manageable complexity. Interestingly, it works out quite reliably in practice, but in detail, the results may differ slightly after each run. Later, we will take a closer look at this phenomenon. So for us who want to do 3D reconstructions in the future, the important lesson remains that we are working with a methodology that is constantly changing and thus can provide better solutions at a later time. This means that here, in particular, we have to pay attention to how we want to deal with it and how we want to store and prepare our data accordingly, especially with regard to the later reproducibility of determined research results. The use of photos has now become established in archaeological documentation technology and has significantly simplified the work. However, photos also cannot replace the step of interpretation. This brings us to the topic of 3D models, or the projections of 3D models. Even if photos are extended by one dimension, we have to be aware that 3D models taken alone without interpretation have no scientific value either. Once again, we maintain that only a comprehensible, well-founded interpretation of a photo or 3D model gives the content an archaeological, scientific value. Nowadays, 3D models of terrain or artifacts can be created quickly and, in some cases, completely automatically. However, the results themselves have no scientific value. For example, this model shows a part of the Orkhon Valley in Mongolia, which is a UNESCO World Heritage Site. The 3D model gets an archaeological value only through the scientifically based human interpretation. Here we see a classification of the still visible building structures in the terrain and a resulting city model of the Uyghur capital Karabalgasyn of the 8th and 9th century. This is what makes this 3D model a remarkable testimony of human history. For now, we should find good arguments and discuss interesting applications that show us what new possibilities arise from the use of 3D models. Let's start the topic of 3D reconstruction with the end of the creation process and the outlook on the actual use and added value of 3D models in the archaeological field. 3D models are very popular as a visual result of a documentation campaign. Who doesn't like to show a detailed moving 3D model of an outstanding find, thus transporting the auditorium of a conference room into another temporal time period? This digital presentation with the comments and background of an expert, and we will come back to this in a moment, is enough for the auditorium. No one would expect to see the original artifact at a conference. Digital models are suitable for presenting results in publications. A common practice is to publish a 3D model on one of the major archaeological platforms. The German Archaeological Institute, for example, offers one of the largest archaeological databases with Arachne and has almost 5 million entries. A very interesting idea is certainly the use of pattern recognition methods directly on an excavation or during the exploration of a site. The ArchAid project, funded by the European Union with almost 2.5 million euros, had the aim of providing a platform for 3D models and metadata, and in parallel developing an app to match new finds on an excavation with those in the database, possibly enabling faster assignment and thus dating. A similar idea is being followed by University of Applied Sciences Dresden in cooperation with the German Archaeological Institute and the State Office for Archaeology in Saxony with the VOC-tree analyzer software. It breaks down objects in the database into features and generates so-called unique fingerprints. This can later also be used to assign fragments of the learned information to known objects. The database currently focuses on the classification of medieval needles, which were provided for this purpose by the State Office for Archaeology in Saxony. With 3D models, we have a digital representation available that we can further process in various ways to make useful information visible. This example was taken during a documentation campaign in the Orkhon Valley in Mongolia in 2018. The representation of the terrain height in digital numerical form allows numerous mathematical manipulations to make even the finest structures visible in the model. Here we can see some results. Image A, a pure aerial photograph with a section of about 1 square kilometer, initially shows no signs of human settlement remains here. Image B, also a vegetation model, does not provide any indications here. Image C, only a false color representation of the 3D model in relation to the given height differences, makes structures visible. Image D, one of these structures shown in an enlarged view. Image E, a measurement of the height course on a length of 30 meters shows. Here a difference in height of nearly 25 centimeter on 30 meter. This is not visible in the field as a human observer simply because of the vegetation. Image F. The symmetrical structure can now be indicated over an area of almost 1 hectare. Image G, the structure visualized in the original representation, provides a starting point for further investigation. In order to show the diversity and possibilities of applications, a few examples have been briefly selected here that do not originate directly from the archaeological context. Let's take a look at a reconstruction in the museum context as an example. A GoPro Hero 3 was used for the reconstruction of an approximately 150 million-year-old skull in the Berlin Museum of Natural History. From a 25-second video with a resolution of 1080p and 60 fps, 800 images were automatically extracted and combined into a model. In this case, the skull was already well prepared for the recordings due to its exposed positioning and illumination. For comparable objects, it is difficult to find the correct position without damaging the object. In these cases, it often helps to take images from several sides, with the same diffuse illumination, and to make sure that the transitions of the sides to each other must also be treated as one recording set. Sometimes subsequent processing of the reconstruction result is necessary. After processing the model, cropping and lighting, the digital reconstruction of the skull is available with a detailed density in the millimeter range. As another example, let's look at the reconstruction of a human from the 2016 CNN broadcast. Journalist Nick Glass amazingly had no problem staying absolutely still for 3 to 5 minutes, serving as a good 3D model for the Videogrammetry's usability in practice. An important tool in taking photos and videos for 3D photogrammetric reconstructions are the multicopters available today. They allow the capture of images from a variety of perspectives and from higher altitudes. In addition to the difficult and, more importantly, safe flight maneuvers that had to be performed manually in a small space to capture Nick Glass, the challenge here was the extreme sunlight and reflective portions of the bench. As a result, the poor structure of the bank is clearly visible. Interestingly, this example gives us a good candidate for an important rule in the business of 3D reconstruction. Always keep the original images, document the reconstruction steps used, and save the 3D model. By saving the original images and processing more than 5 years after this result, we find that a new 3D reconstruction with the original data can lead to a much better result. This concrete example shows once again that we should perceive the 3D reconstruction process as a constantly changing chain of algorithmic procedures with ever better solutions. The final result can be seen here. Amazing! After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own. The practical task here is to become familiar with the free program Visual SFM and to try out the first stage of creating a 3D model. A dataset from Denmark is available. Here we see the individual steps of the processing and a first impression of the result. The second dataset available is the images of a turtle, which can also be processed. Afterwards, it would be interesting to think about a useful folder structure and to make a suggestion.